So, question number 19 and problem number 22. On question 19, it says the car is traveling at 20 meters per second. The driver applies the brakes and the car slows down with an acceleration of negative 4 meters per square second. What is the stopping distance? So, I just draw out for myself just so I make sure I understand what's happening in the problem. We got a car slowing down, coming to a stop. So, that velocity they gave you is the initial velocity. You're coming to a stop, and they gave you the acceleration, 4 meters per second per second. They wrote it as 4 meters per second squared, but that's the same as meters per second per second. So they're slowing down 4 meters per second every second, is the way you can think of that. And they want to know the stopping distance. So, we look at our equations, and we want one that doesn't have time. And it's going to be this one. And we know the final velocity is 0, so throw that out right away. And your job is to solve for d, so let's move this over. Get rid of anything adding or subtracting first. Equals 2ad, subtracting v0 squared from both sides. Divide by 2a. Divide by 2a. And we get a formula now for the distance. It's the initial velocity squared divided by 2a. And what have we got here? The negative of 20 meters per second squared divided by 2 times negative 4 meters per second. And solving that, you're going to have a negative up top, but you're going to have a negative in the denominator. It's going to end up being a positive answer. I don't know what it is. Actually, you can probably work it out without even a calculator here. And the units, you've got, I'll just look at that over here. I've got meters per second squared, so it's meters squared, second squared, divided by meters per square second. Well, look at what cancels out. The second squareds go. That meters knocks out one of those meters. Your answer will come out in meters. And we're good. Question 22. They gave you, back on problem 16, a velocity time graph for the blood rushing through the, where is it? In the ascending aorta during 1 heartbeat. It speeds up, and then it slows down. It speeds up, and then it slows down. It speeds up, then it slows down. Every time your heart beats. And I made a quick copy of that graph here. You're better off using the one in the book because mine's off. It's a lot more lopsided in the book. And on 16, they were after how far does it travel. So there, if you have a velocity time graph and you're after displacement, you want to look at the area under the curve. In this case, that triangle. On 22, they're asking you to find the acceleration. It speeds up and it slows down. Both of those are accelerations. And so we need to find the slope. And you're just going to do slope calculations here. Or truly the definition of acceleration, the change in velocity over the change in time. Our change in velocity, and here's where you're going to have to estimate a little bit. I would say that's going from 0 up to about 0.75. So final 0.75, I assume this is meters per second, minus 0 over, now here's where you got to be careful here, that time. It's starting out here at 0.2, and I'm looking in the book here at it. I would say it's probably somewhere around 0.27 where the top of that graph is. And that's going to be an estimate. So my change in time, 0.27 minus 0.2. These are in seconds. And calculate away. 0.75 meters per second divided by 0.07 seconds. And you'll get your acceleration in meters per square second. Because meters per second divided by seconds gives you another seconds in there. And my answer should come out positive. I've got a positive slope here. I should have a positive acceleration. On the way down, now we'd expect a negative. My change in velocity, well, now I'm going from 0.75 down to 0, so I'll say 0 minus 0.75 meters per second. Over, well, if this was a 0.27, now I've got 0.4 minus 0.27, and you're going to end up with a negative answer here. You're going to have a negative number up top, but a positive number in the denominator. Seconds there. And I'll leave the calculation to you. And it will again be in meters per square second. Looking at it in the book, I would expect a bigger acceleration, number-wise, like absolute value-wise, for the blood initially moving. A smaller acceleration as it slows down. That doesn't seem as steep as the first one. And you should see that in your numbers, because here you've got a much shorter time span. If it takes place over a smaller number in the denominator, you're going to get a bigger answer. So a bigger acceleration as the heart starts to beat and then slowing down. Not as big an acceleration. And it is negative. All right, that's those two. Have a good day.